Hello friends. So in this session we'll try to understand very important concept of the heat transfer, that is Reynolds-Colburn analogy. It is the analogy between fluid friction and heat transfer. So basically why we use it, the main purpose of Reynolds-Colburn analogy is that we want to find out the heat transfer coefficient with the help of fluid friction or the friction coefficient. With the help of, we want to derive a relation between the fluid friction or local friction coefficient and the local convective transfer coefficient, so that we can find out by knowing the friction coefficient. So let us see how we can do this. Let's say we have a plate and there is a boundary layer formation on it. This is the hydrodynamic boundary layer. Okay, let's say this is our x-axis, this is y-axis, and this is our velocity profile. Fine. At a location of x, we have a velocity profile. Now, let's say TW is our tau W is our local wall shear stress. And how we can define it? That will be equal to mu del u by del y at y is equal to 0. But in the previous session, what we have derived, or we know that, from the concept of the hydrodynamic boundary layer, we have derived the velocity profile, and by that velocity profile, we can calculate the velocity gradient. So velocity gradient, if we'll calculate, then this will come out to be uh, V infinity 3 by 2 delta. If you'll see that that video in which I have derived the velocity profile, first I have derived the momentum equation for the hydrodynamic boundary layer, and by that equation we can derive the velocity profile, and by that velocity profile or function of velocity, that is, from this we can find out this velocity gradient with respect to y. So we can say that the tau wall will be equal to mu v infinity 3 by 2 delta. V infinity is our free stream velocity. Fine. Or we can say that, because we know that delta is equal to 5x upon, from the Blassius solution, right, by root of Reynolds number, then this can be written as mu v infinity 3 upon 2 5x divided by Rex. Fine. So if we want to find out tau wall shear stress from the concept of the fluid mechanics, so we can say that from fluid mechanics concept, the local shear stress tau wall can be written as CFX local skin friction coefficient into half rho infinity square. Shear stress can be written like this, where CFX is the local skin friction coefficient or local drag coefficient. This is a dimensionless parameter. This CFX is comes out to be 0.004 or 0.005 for the case of pipe, where HF is equal to FL V square upon 2GD. HF is what? It is the head loss due to friction, and F is what? This is the Darcy friction factor, or and we this head loss we can find out from the Moody's diagram also. So by equating these two terms from equation 1 and from equation 2, equating 1 with 2, we'll find Cfx by 2 is equal to 0.332 Reynolds number raised to the power minus half. Okay, and we know that Nusselt number is equal to 0.332 Reynolds number raised to the power half and Prandtl number power cube root. Fine. Let us divide both equation by Reynolds number and Prandtl number. Local Reynolds number and Prandtl number. Okay. Now this term is called as Nusselt number divided by Reynolds number into Prandtl number is called as Stanton number. This is the new number defined. Fine. So if we'll write down all the terms like Stanton number is equal to Nusselt number. Nusselt number is written as Hx divided by k. Reynolds number is written as V infinity x rho by mu into Prandtl number is equal to mu Cp upon k. So Stanton number is actually Hx upon rho V infinity Cp. Fine. And combinedly Reynolds number into Prandtl number is also called as Peclet number. This is called as Peclet number. Fine. Or so we can say that Stanton number can be also written as Nusselt number divided by Peclet number. Fine. What is the need of Peclet number to define here? Peclet number is actually used in the liquid metal cooling. So Peclet number is significant in liquid metal cooling of nuclear reactions. That's why we have defined here. In some further session, I will explain all these numbers, that what is the significance of all these numbers and how we can use that. So now we have got that Stanton number is equal to 0.332 Reynolds number power minus half and Prandtl number power minus 2 by 3. Because we have divided here, when we write, then we'll get this. And earlier we have got by equating two equation, that is Cfx by 2 is equal to 0.332 Reynolds number power minus half. Okay, now replace it here, then we'll get Stanton number, local Stanton number is equal to Cfx by 2 into Prandtl number raised power minus 2 by 3, or we can write it as Stanton number, local Stanton number into Prandtl number power 2 by 3 is equal to Cfx by 2. This is very important equation, and this is called as Reynolds Colburn analogy. So here you can understand that here what is Stanton number? Stanton number is equal to Hx upon rho V infinity Cp, and it is directly related to Cfx. So by knowing Cfx, local skin fraction, we can find the local heat transfer coefficient. This is the main fundamental of the Reynolds Colburn analogy. Thank you.